In this video, we're going to do an example of how to use the Van Deemter equation in order to determine the optimal flow rate in a column chromatography experiment. For this problem, we are going to be given three different chromatograms obtained at three different flow rates to determine what is going to be the best flow rate for maximum resolution. In this case, we see the first chromatogram has three components, but we're really only going to be concerning ourselves with the first peak because we only need one peak in order to do this particular calculation. This first chromatogram was obtained at a fairly low flow rate of 5 milliliters per minute. And under those conditions, the first component had a retention time of about 4.4 minutes. The width at half height, I can estimate using the bottom scale at about 0.4 minutes. If we look at the second one, we see that I've increased the flow rate to 12 milliliters per minute, and the retention time has gotten shorter because of the higher flow rate to be 3.2 minutes. And in the last one, I've really jacked up the flow rate to about 15 milliliters per minute, and the retention time is now down to about 2.2 minutes. For each of these chromatograms, we can calculate the number of equilibria that must have occurred in order to create that particular peak, using the equation discussed earlier, where n is equal to 5.54 T prime r divided by width at half height squared. If we substitute in the values for this particular chromatogram, we can see that the number of equilibria that must have occurred in order to have that width at that retention time is about 670 equilibria. Because we know the height equivalent of the theoretical plate is the length of the column divided by the number of equilibria, we can determine that at a flow rate of 5 milliliters per minute, the height equivalent of a theoretical plate is about 3 millimeters. That means every 3 millimeters of column, you're undergoing one equilibrium. In the second experiment, we have sped it up a little bit, which is going to reduce the amount of longitudinal diffusion. And under those circumstances, we can see that the number of equilibria has actually increased to about 1,400. So we've almost doubled the number of equilibria. And now the height equivalent of a theoretical plate at 12 milliliters per minute has been reduced to about 1.4 millimeters. This is going to produce better resolution because of the smaller height equivalent of a theoretical plate producing a greater number of equilibria. Finally, when we increase the flow rate to 15 milliliters per minute, now mass transfer starts becoming a problem. So the number of equilibria has gone down to 670. If we calculate then the number of equilibria generated at 15 milliliters per minute, then we get a height equivalent of a theoretical plate of 3 millimeters once again. So under these circumstances, we have three flow rates and three height equivalents of a theoretical plate. From that, we can write three Van Deemter equations because we know that HETP is the A constant plus B over V plus CV, which means from the first chromatogram, we had a height equivalent of a theoretical plate of 3 millimeters, which is going to be A plus B over the flow rate of 5 plus C times 5. Number 2 It's giving us 1.4 millimeters is the HETP, and that's going to be A plus B over 12 plus C times 12. And number 3, HETP was 3 millimeters, and that's still going to be the constant A plus B divided by 15 plus C times 15. Hopefully, at this point, you can see that we have 3 equations and 3 unknown constants. You can solve these 3 equations simultaneously using algebra, of course. It might get a little bit messy, or you can do it using a matrix approach. In this case, the matrix would be 1, the constant here, 1/5, and 5 would be the constants. In the second one, constants are 1, 1 over 12, and 12, 1, 1 over 15, and 15. And the answer matrix is 3.0, 1.4, 3.0. If you use that approach, you can use Excel to multiply the inverse of this matrix by that matrix. This is actually the inverse of this matrix. So if we multiply this times that, it will actually solve the simultaneous equations for us and give us the constants A, B, and C without having to do the algebra. From this, we can determine that the Van Deemter equation is the height equivalent of a theoretical plate is the A constant, minus 14.8, plus the longitudinal diffusion effect, which would be the B constant, 67, divided by its velocity, plus the mass transfer constant, which would be 0.89 times the velocity. This gives us the equation of the line. So we could actually just have Excel then calculate the different HETPs at the different velocities, and then plot HETP as a function of velocity, and we get what we recognize as the Van Deemter plot. Maximum resolution is going to occur at the minimum HETP. You can see from here it's going to be in this area. That flow rate is going to give us the best possible resolution because it will maximize the number of equilibria. Or you can simply look over here and see that the minimum HETP, or maximum resolution, so V optimum for this particular column is 9 milliliters per minute. And at that flow rate, we are going to have the optimal resolution.